Imagine for a moment that you are learning to count, and instead of using the usual digits 0 through 9, or even just 0 and 1 like computers do in binary, you are given 3 little building blocks. One is 0, which is nothing, one is +1, which is something, and one is -1, which is the opposite of something. This is the world of balanced ternary arithmetic, a way of writing and thinking about numbers where your digits can go positive, neutral, or negative. At first, this sounds strange. Why would we ever want digits that can be negative? Doesn't that just make life more complicated? But when you look closer, you realize that it actually makes certain things simpler, almost as if the universe itself likes balance. Let's imagine you are stacking blocks. In normal math, if you want to cancel out a block, you have to take it away. But in balanced ternary, you already have a special block for taking away. You just place a -1 block right next to a +1 block and they cancel perfectly, leaving only the 0 block. That means the system itself always contains its opposite, built right into its very foundation. It's not just numbers, it's numbers and their shadows, numbers and their reflections. Now think about how we usually do subtraction. If I ask you to do 7 minus 5, you might count up to 7, then take away 5. That works, but it feels like work. In balanced ternary, subtraction is simply the same as addition, because the -1 digit is already part of the alphabet. You don't need to invent a new operation. You don't need to think of subtraction as something extra. It is baked in, like the shadow is part of the light. Take a moment to reflect on this. What if our own way of thinking about good and bad, or up and down, or positive and negative, were as natural to us as breathing, never needing special explanations? Balanced ternary shows us what it's like to live in that kind of symmetry. There's another curious thing. Computers today mostly run on binary, using just 0 and 1, on and off like switches. But back in the 1950s and 1960s, there were actually computers built with balanced ternary logic. These machines used -1, 0, and +1 as their language. And here's the surprising part. They were often more efficient at certain tasks than binary computers. Because with balanced ternary, you sometimes need fewer steps to represent big numbers. The system feels closer to nature in some ways because it doesn't always push everything into just yes or no, but allows for a middle path and an opposite path too. Balanced ternary also avoids certain awkward situations we have in binary. For example, rounding numbers can feel cleaner. Instead of always shifting up or down, balanced ternary has a way of letting the digits find their own natural balance. Imagine a scale that always settles evenly instead of tipping one way or the other. It feels less forced, more organic. But the strangest and most beautiful part is how elegant the system looks when you use it. Numbers that look messy in decimal or binary can sometimes look almost artistic in balanced ternary, like patterns unfolding with symmetry. It's as if the numbers are whispering, there is another way to count, another way to see the world. Of course, we don't use balanced ternary today in most places. Binary has won because it's simple to build in physical machines. But that doesn't mean balanced ternary isn't important. It remains like a hidden treasure, a reminder that our normal way of counting is not the only way. There are other paths, other systems, other balances we can choose to explore. Have you ever wondered what would happen if every number had a faint shadow following it? A part that is not fully there but still changes the way the number behaves? This is the strange world of dual numbers. At first they look simple. You take an ordinary number, like 3, and then you add a special shadow piece to it. We write it as 3 plus something times epsilon. Epsilon is not like an ordinary number. It is a special symbol, so small and strange that when you multiply it by itself, it disappears. Epsilon times epsilon equals 0. Imagine a shadow so thin that if you try to stack it on itself, it vanishes completely. So a dual number looks like this, a plus b times epsilon. The a is an ordinary number, the solid visible part. The b times epsilon is the shadow, tagging along. You can think of it like a person and their reflection in the water. The person is real and solid while the reflection is softer, almost an echo. The reflection doesn't act on its own, but it changes how we see the person. Together they form something new, the dual number. Why does this matter? Because dual numbers let us handle tiny changes, the kind of changes that are almost invisible. Imagine walking up a hill. At every step your height above the ground increases, but only slightly. Dual numbers can capture that slightly in a precise way. The epsilon shadow part carries the story of change, slope, and direction. In fact, dual numbers are used in something called automatic differentiation, which is how computers can instantly calculate slopes of functions. It is as if the shadow part quietly keeps track of the way things are moving, even when the main number just stands there. Think about what this means. In our usual arithmetic, a number is just a single point, a place on the line. But in dual arithmetic, each number is like a point with a whisper attached to it, a solid core and a hint of movement. Instead of seeing numbers as frozen, dual numbers let us see them as alive, always ready to shift. The epsilon part doesn't show up in ordinary multiplication or addition the way you'd expect. Because epsilon squared equals 0, The shadow never grows heavy, it never takes over, it only nudges, suggests, reminds, a small presence that cannot be ignored. Why is this unsettling? Because it suggests that even the simplest number may not be alone. It may have companions, layers, echoes. Mathematics, we often believe, is cold and exact. But dual numbers show us that it can also be soft, suggestive, almost ghostly. They remind us that numbers don't just measure size. They can also measure change, possibility, and potential. Take a moment to reflect on this. A world where numbers walk with shadows, where multiplying a shadow by itself makes it vanish, where every number has both a body and a whisper of movement. Dual numbers expand arithmetic into something more than calculation. They reveal a hidden dimension, one that is fragile, fleeting, and yet deeply powerful. In the quiet of this thought, we begin to see numbers not just as answers, but as companions in a world of constant change.
Have you ever thought about what it would be like if numbers didn't just move forward and backward on a line, but could spin, twist, and turn in space? That is the strange and beautiful idea behind Quaternions. At first, they look like just another kind of number, but they are far more than that. Instead of being built from one piece, like ordinary numbers, or two pieces, like complex numbers, Quaternions have four parts. You can imagine them written as a plus b times I plus c times j plus d times k. Here, a, b, c, and d are ordinary numbers, and I, j, and k are special directions. Together they make something that is not just size, but orientation, numbers that can describe movement and rotation. To see why this matters, think about turning a key in a lock, or spinning a ball in the air. Ordinary numbers can't describe these turns. They can measure how far you go, but not how you twist. Even complex numbers, with their ability to spin on a flat plane, stop short once you want to describe full 3D motion. Quaternions step in here. They give us a way to encode rotations in 3 dimensions, capturing the way things turn in space without confusion. But Quaternions are not like other numbers. When we multiply ordinary numbers, the order doesn't matter. 2 times 3 is the same as 3 times 2. But in the world of Quaternions, order matters. Multiplying I by j gives k, but multiplying j by I gives negative k. This property is called non-commutative. At first it feels wrong, like a rule has been broken, but in reality it is a deeper truth. In the real world, turning left and then forward is not the same as turning forward and then left. Quaternions mirror the real logic of movement. Why is this so powerful? Because Quaternions are used everywhere that rotation matters. They guide airplanes through the sky. They steer spacecraft across the emptiness of space. They even control how 3D characters move smoothly in video games and movies. Without Quaternions, many of the rotations we take for granted would be clumsy, unstable, or impossible. Yet there is also something mysterious here. When William Rowan Hamilton, the mathematician who discovered Quaternions, realized how they worked, he was walking across a bridge in Dublin. Legend says he was so struck by the beauty of the idea that he carved the formula I squared equals j squared equals k squared equals I times j times k equals -1 into the stone of the bridge. It was as if he had uncovered a secret door in the world of numbers, one that connected arithmetic with the very fabric of space. Take a moment to reflect on this. Numbers that no longer just count but twist. Numbers that hold not only magnitude but direction. Numbers that refuse to follow the old rule that order doesn't matter, because in the real world of turning and spinning, order matters deeply. Quaternions remind us that arithmetic is not only about abstract puzzles, it is about finding the hidden structures that make our universe move. They are numbers with direction, numbers that whisper the logic of rotation, numbers that expand what arithmetic can mean. Have you ever noticed how in math we are told that the order of grouping doesn't matter? If you add 1 plus 2 plus 3, it doesn't matter if you add 1 and 2 first, or 2 and 3 first, you always end up with 6. This rule is called associativity, and it feels so natural that we don't even think about it. But what if there were numbers where this rule broke down? What if you grouped them differently and got completely different results? This is the bizarre world of Octonions, a kind of number system that refuses to obey the usual law of associativity. To understand Octonions, let's go back a step. Ordinary numbers are simple, they have just one part. Complex numbers are richer, they have 2 parts, a real and an imaginary. Quaternions go further, 4 parts with I, j, and k acting like directions. Octonions stretch this idea even further, doubling the Quaternions into 8 parts. Imagine a number that looks like a plus b times e1 plus c times e2, all the way up through 8 pieces, where each piece is tied to a different symbol. It's like a number split into 8 different voices, all speaking together. But here is where it gets strange. With Quaternions, multiplication was already unusual because order mattered, non-commutative arithmetic. With Octonions, it gets even stranger. Not only does order matter, but the way you group things matters too. For example, if you multiply x times y times z, you might get a different answer than x times y times z.
This breaks the comfortable rule we learned in school. At first it feels impossible. How could arithmetic survive without such a basic law? But Octonions do survive, and they open a door to a very unusual universe. Why do mathematicians care about Octonions? Because they appear in surprising places. They are linked to certain patterns in geometry and in high-level physics, especially in theories that try to describe the most fundamental particles and forces. Octonions are connected to mysterious shapes called exceptional Lie groups, which show up in the mathematics of string theory. These ideas are at the cutting edge of trying to understand the deep fabric of reality. It's as though Octonions are a hidden language the universe whispers, one we barely understand but know must be important. Think of it like this: in ordinary arithmetic, the rules feel like solid ground beneath our feet. In Quaternions, the ground tilts slightly, because order matters. In Octonions, the ground shifts and bends as we walk, because grouping itself matters. It is disorienting, but it reveals that arithmetic is not one fixed thing. It is a spectrum of possibilities, each stranger and more expansive than the last. Take a moment to reflect on this: a system where numbers refuse to be neatly grouped, where order and structure slip away from our grasp, where 8 different parts of a number collide and twist in unexpected ways. Octonions remind us that arithmetic is not a finished story. It is a vast and evolving landscape, where even the rules we thought were unshakable can bend. In the quiet of this realization, we see numbers not as rigid truths, but as shifting shadows of a much deeper mystery. What happens when we keep pushing numbers further and further into new dimensions? First came the real numbers, the ones we use every day. Then complex numbers, which added a twist with the imaginary unit. Quaternions expanded this into 4 parts, and Octonions stretched it into 8. But mathematicians didn't stop there. They asked, what if we go further still? That's where Sedanions come in, numbers that live in 16 dimensions at once. It sounds almost impossible. How can a number have 16 pieces? Imagine holding a box, and inside are 16 little compartments. Each compartment holds a part of the number. Some are familiar, like the real part. Others are new, each with its own symbol, like E1, E2, E3, all the way up to E15. When you put them together, they form a single Sedanion. It's like a choir with 16 different voices, all singing in harmony, or sometimes in dissonance. But here's where things become really strange. With ordinary numbers, everything felt stable. Even with complex numbers, the rules held firm. With Quaternions, the ground shook a little. Multiplication no longer worked the same way depending on the order. With Octonions, it got even shakier. How you grouped the numbers mattered. With Sedanions, the ground almost disappears beneath your feet. They lose some of the nice properties that made earlier systems so special. In fact, in Sedanions, you can multiply 2 non-zero numbers and end up with 0. This never happens in normal arithmetic. Think about that. Something times something equals nothing. This strange property makes Sedanions feel wild, almost chaotic. They don't behave the way we expect numbers to behave. It's like entering a dream world where the rules of logic start to dissolve, and yet they still exist. They're still part of the grand family of number systems. Even if they seem unruly, they show us that arithmetic doesn't have to stop at the boundaries we thought were fixed. Why should we care about such unruly numbers? Because they teach us humility. They remind us that math is not simply about order and neatness. It is about exploration, about wandering into new lands, even when those lands feel unstable. Sedanions may not have the same usefulness as Quaternions in physics or geometry, but they are a natural step in the chain. They show what happens when we keep doubling, when we keep expanding dimensions. They reveal not just beauty but also fragility. The way rules we thought were eternal can vanish the further we stretch them. Take a moment to reflect on this. A world where numbers expand into 16 dimensions, but lose the order and structure that kept them steady. It's unsettling but also freeing. It tells us that numbers are not just tools but landscapes to be discovered, each with its own laws, its own surprises, its own mysteries. Sedanions may not play by the rules, but in breaking them, they remind us that even in mathematics there are worlds beyond the safe and familiar. When we first learn about numbers, they feel simple. You start with whole numbers, 1, 2, 3. Then you meet negative numbers like -1 or -5. Later, fractions come in, numbers like 1/2 or 3/4. Just when you think you know the world of numbers, something strange appears. The imaginary unit, usually written as I, which is defined as the square root of -1. It doesn't seem real at first, but it opens the door to complex numbers, which are combinations of ordinary numbers and I. A complex number might look like 2 plus 3i, which means 2 in the real direction, and 3 in the imaginary direction. Now imagine taking all of these complex numbers and focusing only on the ones where both parts are whole numbers, no fractions, no decimals, just integers. So you might have 1 plus 2i, or -3 plus 0i, or 5 plus 7i. These special numbers are called Gaussian integers. You can think of them as points on a grid. The horizontal line is the real part, and the vertical line is the imaginary part. Put them together and you get a checkerboard that stretches forever in all directions. Each square on the board represents a Gaussian integer. This changes how arithmetic feels. When you add or subtract Gaussian integers, you just move along the grid like walking north, south, east, or west. When you multiply them, the grid spins and stretches in surprising ways. For example, multiplying 1 plus I by 1 plus I gives you 2i. Multiplying 2 plus I by 3 plus I gives you 5 plus 5i. It's like a dance between numbers where each step combines direction and magnitude. But here's the fascinating part. Gaussian integers don't just sit there quietly. They carry their own version of prime numbers. In ordinary arithmetic, primes are numbers like 2, 3, 5, 7, numbers that can't be broken down into smaller pieces except by 1 in themselves. In the land of Gaussian integers, new primes appear. For example, the number 5, which is prime in ordinary arithmetic, breaks down into Gaussian primes. It can be written as 2 plus I times 2 minus I. Suddenly, the simple number 5 is not so simple anymore. This idea that even prime numbers change shape when you step into a new world feels unsettling but also beautiful. It tells us that primes are not universal in the way we once thought. They depend on the system we live in. What feels indivisible in one world can split apart in another. Gaussian integers reveal hidden cracks in what we thought were solid walls. And this isn't just a math curiosity. Gaussian integers matter in real life too. They appear in coding theory, in designing error-checking systems that keep our digital messages safe. They also help in cryptography, the science of protecting secrets. Their grid-like structure makes them useful for creating patterns and solving puzzles that ordinary numbers alone cannot handle. Think of it this way. When you look at Gaussian integers, you are standing on an endless city made of squares. Each building in that city represents a number with a real part and an imaginary part. Walking through it feels familiar yet strange, because the rules of factorization, of primes, of arithmetic itself, all shift. Gaussian integers remind us that numbers are not a single rigid world, but many layered worlds, each with its own secrets. Most of the numbers we know, like 1, 2, or 3, were created to count things. Apples, coins, stars in the sky. Later, other numbers appeared to solve problems. Negative numbers for debts, fractions for sharing, imaginary numbers for equations that refuse to behave. But there is one family of numbers that wasn't born from counting or measuring. Instead, they were born from games. These numbers are called Nimbers. The story begins with a simple game called Nim. Imagine you have a few piles of stones. On your turn, you can take away as many stones as you want, but only from one pile. Then the other person takes their turn, and so on. The person who takes the very last stone wins. The game seems like it's only about luck or quick thinking, but hidden inside it is a secret arithmetic, a whole new way of adding numbers together. That's where Nimbers come in. Nimbers are numbers built to describe who has the advantage in these kinds of games. They don't follow the usual rules of addition that we learn in school. Instead of carrying digits or multiplying as usual, Nimbers follow a strange process that comes from patterns of winning and losing positions in the game. For example, if you add one stone pile to another using Nimber arithmetic, the result might not be 2 like we'd expect. It could be 0. That's because in the logic of the game, one pile plus another identical pile cancels out the advantage, just like two equal forces balancing each other out. This feels strange at first. We're used to thinking of numbers as solid and predictable. 1 plus 1 is always 2. But Nimbers teach us that arithmetic depends on context. In the world of games, 1 plus 1 is 0. A move plus the same move cancels itself out. It's like shadows overlapping. The moment two identical shadows fall on top of each other, they disappear into darkness. Nimbers go even further. They can grow into enormous structures that describe not just one game, but all possible games of this kind. Each Nimber represents a position, a state of balance or imbalance. When you combine Nimbers, you are really asking, if I put these two games together, who has the winning strategy now? It turns arithmetic into strategy, and numbers into moves. This has powerful consequences. Nimbers don't just explain Nim. They form the foundation of a field called combinatorial game theory, which studies all sorts of games, chess puzzles, board games, even abstract systems with rules that don't look like games at first. Nimbers become a universal language for describing fairness, balance, and strategy. And here is the mind-bending part. Nimbers are actually connected to some of the deepest areas of mathematics. They link to surreal numbers, an even larger system that includes ordinary numbers, infinitesimals, and infinities. Nimbers are like one corner of that grand universe, a corner that happens to grow out of something as playful as a game with stones. Think about that for a moment. Children playing a simple game could, without knowing it, be acting out the logic of an entirely new number system. Something as lighthearted as taking turns with stones turns into a window into the infinite. Numbers don't have to be born from counting sheep or measuring lines. They can be born from play. They can emerge from laughter, competition, and strategy.
Imagine you are playing a game where numbers don't go on forever in a straight line, but instead wrap around in a circle. This is what modular arithmetic does. If you are counting on a clock, after 12 comes 1 again. That's modular arithmetic with 12 as the size of the circle. 7 hours after 9 o'clock doesn't give you 16 o'clock, it gives you 4 o'clock. The numbers bend back on themselves. Now, when the circle size, the modulus, is a prime number, things work very smoothly. Every number except 0 has a neat partner that acts like a division helper. For example, in modular arithmetic with 7, the number 3 has a partner 5 because 3 times 5 is 15, and 15 wraps back around to 1. This makes division possible, even though we are on a circle. It feels neat, balanced, and complete. But what happens when the modulus is not prime? When the size of the circle is a number like 12, or 15, or 20? Something strange happens. Division begins to break down. Some numbers no longer have partners. For example, in the world of 12, try dividing by 2. It doesn't behave in the usual way. 2 times 6 is 12, which is the same as 0. Suddenly, multiplication can collapse numbers back into 0, even when neither number was 0. These are called zero divisors. They are like hidden traps in the circle, where the normal rules of arithmetic stop working the way we expect. Take a moment to think about that. In ordinary arithmetic, the only way to get 0 from multiplication is to include 0 itself. But in modular arithmetic with composite moduli, meaning the modulus is not prime, ordinary numbers can suddenly behave like imposters. 6 times 2 in the world of 12 is 0, even though 6 and 2 are both perfectly fine numbers. It feels like the ground beneath your feet is not solid anymore. This broken division changes everything. It means we can't rely on the usual structure of arithmetic. We can't always solve equations. Some problems that have clear answers in the prime world suddenly have none in the composite world. Imagine trying to open a lock with a key, but the key keeps crumbling into dust when you turn it. That's what division feels like here. And yet this brokenness is not useless. In fact, it is deeply important. Cryptography, the science that protects your bank account, your passwords, and your private messages, often uses modular arithmetic. The strength of certain codes depends on the fact that division is tricky, and sometimes impossible when the modulus is composite. What feels like a bug in the system is actually a feature that keeps secrets safe. So modular arithmetic with composite moduli is a strange world. Numbers still march around a circle, but the music they march to is uneven. Some notes vanish into silence, others repeat in odd ways. Division, that reliable tool, no longer always works. It's as if arithmetic itself is reminding us that not all worlds are clean and tidy. Some are messy, filled with traps and puzzles. When you step into this world, you learn that arithmetic is not a single set of unshakable rules. It's a collection of different games, each with its own surprises. And sometimes, the most surprising games are the ones that bend the rules until they almost break. Division. It sounds so simple, right? You take one number and try to see how many times another number can fit inside it. But what if I told you that in some strange number systems, division does not work the way you expect? What if I told you that sometimes dividing by a number is impossible, unless you play by new rules that feel almost like magic tricks? This is the world of modular inverses, a place where dividing is not really dividing, but something stranger, something hidden inside the structure of numbers themselves. Let's start small. Imagine you are working with a clock. A clock only goes up to 12 hours and then it resets back to 1. This is modular arithmetic. 12 plus 1 is not 13, it is 1. 12 plus 2 is not 14, it is 2. You see, the clock does not care about the whole number line, it only lives inside its own little circle. Now imagine someone asks you, can you divide numbers on this clock? At first you might say, of course you can. But here is the problem. Sometimes division simply does not make sense. For example, try dividing 2 by 2 on a 12-hour clock. Normally you'd expect the answer to be 1. But wait, on the clock 2 times 6 is also 12, which is the same as 0. Suddenly, things get confusing. If 2 times 6 is 0, then how could we ever undo multiplication by 2? There is no single number that fixes this problem. This is where modular inverses come in. Instead of thinking about normal division, we ask a different question. Is there a number that when multiplied by my number, gives me 1? That number, if it exists, is called the modular inverse. For example, on a 7-hour clock, the number 3 has an inverse. Why? Because 3 times 5 is 15, and 15 is the same as 1 in mod 7 arithmetic. So on this clock, dividing by 3 is the same as multiplying by 5. But here's the twist. Inverses do not always exist. On a 12-hour clock, 3 does not have an inverse. Why not? Because every multiple of 3 lands on numbers like 3, 6, 9, or 0. It never hits 1. So no matter what, you cannot divide by 3 in this world. Division breaks down unless you choose your modulus carefully. If the modulus is a prime number, then every Tungoan number has an inverse.
But if the modulus is composite like 12, which is made of 3 times 4, some numbers simply have no way to divide. This is both strange and powerful. Strange because it forces you to rethink something as basic as division. Powerful because this trick is the very foundation of modern cryptography. Every time you log into a secure website, your computer is secretly performing modular inverse calculations. It is dividing in a world where division looks broken, but is actually controlled. Without this, online banking, digital signatures, and secure passwords would be impossible. So next time you think about division, remember, in some worlds, dividing is not guaranteed. It depends on the structure of the numbers you are playing with. Sometimes division works only if the number has a secret partner. It's modular inverse. And if no partner exists, then division simply vanishes, leaving only questions behind.
Imagine you're playing a game where numbers wrap around like a clock. Once you reach a certain number, you start again from 0. That's what modular arithmetic is. Numbers cycling back like hours on a clock. If the clock has 12 hours, then after 12 comes 1 again. Simple enough. But here's the twist. Not every clock is smooth and well-behaved. Some clocks are broken in strange ways, and that happens when the number we're wrapping around with is not a prime number. When the number you're working with is prime, like 5 or 7, the rules of the game stay neat. Everything has a clean partner, and math feels balanced. But when the number is not prime, like 4, 6, 8, 9, or 10, suddenly things don't work the way we expect. It's as if the gears of the clock slip and instead of smooth ticking, the hands get stuck. Division, for example, which we often take for granted, suddenly refuses to behave. Let's picture this. Suppose we're working with numbers wrapping around 6. In this world, adding is easy. 4 plus 3 doesn't give 7, it gives 1, because we wrap around. Subtraction and multiplication also follow this wrapping rule. But division? That's where the strangeness begins. Some numbers simply don't have partners to divide with. Imagine asking, what number times 2 makes 1? In our normal math, that's simple, but in this broken clock of 6, there is no such number. 2 keeps cycling between even results. 2, 4, then back to 0, never hitting 1. Division collapses, and certain equations just cannot be solved. This is what makes non-prime modulus so fascinating. Prime numbers act like strong building blocks, steady and reliable. Non-primes, however, are shaky. They can be pulled apart into smaller numbers, and that weakness seeps into the arithmetic. Factors of the modulus creep into the system like cracks in a wall, and through those cracks, strange behaviors leak out. Multiplication becomes trapped in loops. Whole sets of numbers lose their balance, becoming unable to interact cleanly. Think of it like a party. If the modulus is prime, everyone at the party has a partner to dance with. No one is left behind. But if the modulus is composite, meaning it can be broken down into smaller pieces, some people stand awkwardly at the edge of the dance floor. They can't find a partner because the rhythm of the music doesn't match them. Division is impossible for them. They're stuck outside of the game. And yet this brokenness isn't useless. In fact, mathematicians study these systems because their quirks reveal deep truths about how numbers are built. Cracks, after all, show you the structure beneath. When modular arithmetic fails with non-primes, it highlights the unique power of prime numbers, which are like the atoms of arithmetic uncut, indivisible, pure. By exploring what goes wrong with composite moduli, we see more clearly why primes are so central in cryptography, coding, and the very fabric of math itself. So what begins as a broken clock, a frustrating failure of division, turns into a lesson about the skeleton of numbers. Non-prime moduli show us instability, but in that instability lies understanding. Every skipped beat, every missing partner is a reminder. Math, like life, isn't always smooth. Sometimes it's the oddities, the failures, the breakdowns that tell us the deepest truths. Take a moment to think about that. When division collapses, the system is still speaking. It's telling us what makes it weak, and in turn what makes prime strong. In a way, the silence of missing answers is as meaningful as the answers themselves. Imagine you have a big basket of candies. There are so many that counting them one by one feels impossible. Now imagine instead of counting the whole pile, you split the candies into smaller baskets, each one with its own special rule for how many it can hold. Maybe one basket only counts in groups of 5, another in groups of 7, and another in groups of 11. You don't keep track of the full number of candies anymore. You only note how many candies are left over when you divide into those baskets. And here's the strange part. If you know the leftovers in each basket, you can actually figure out the exact number of candies in the big pile without ever counting them directly. This is the heart of something called the residue number system. It is like living in parallel counting worlds, each with its own set of rules. Instead of one straight path of numbers, you walk many smaller paths at the same time. Each path feels simple and easy to follow on its own, but when you combine them, you unlock surprising power. Why is this powerful? Because working with giant numbers can be slow and painful.
Think about multiplying huge numbers with long carries dragging across the page. In a residue system, you don't struggle with the giant number. You break the problem apart into smaller, easier pieces, solve them separately, and then magically stitch the answers back together. It is like breaking a heavy rock into smaller stones, moving them one by one, and then rebuilding the rock at the other side. Let's picture it with something simple. Suppose we want to work with the number 100, but instead of thinking about it directly, we split it into three worlds: the world of threes, the world of fours, and the world of fives. In the world of threes, 100 looks like 1, because 100 divided by 3 leaves a leftover of 1. In the world of fours, 100 looks like 0, because it divides evenly. In the world of fives, 100 looks like 0 as well. So instead of dragging around the number 100, we carry the much smaller pieces, 1, 0, and 0. If you had those three small leftovers written down, you could still reconstruct the fact that the real number was 100. But here's where it feels magical. Operations like addition and multiplication become simpler because they happen inside each small world separately. Additions don't spill over into messy carries, and multiplications don't balloon out into pages of digits. It's clean, tidy, almost too good to be true. And this system isn't just for fun, it's used in places where speed matters: computer chips, encryption, digital signals, things that must handle giant numbers but can't waste time wrestling with them directly. Yet there's a catch. Residue arithmetic is like juggling. As long as you keep the balls in the air, everything looks smooth. But making sure you combine the pieces correctly at the end requires precision. One wrong leftover, one small mistake, and the whole picture collapses. It shows us something deep. Even when breaking down the biggest problems into small ones, you must keep track carefully, or else the truth of the number is lost. So pause here. Think about this. Instead of one number, you can hold many smaller shadows of that number, each living in its own little world. When put together, they tell the full story. Numbers are not just straight lines marching forward. Sometimes they are mirrors, reflections scattered across many worlds, waiting to be pieced together again. Have you ever noticed how natural the number system feels to us? 10 digits, then we roll over, carrying into the next place. It feels obvious, almost like it had to be this way. But what if I told you that 10 is not the only way to count? That there exists a number system where instead of building everything on tens, the building blocks come from factorials, numbers like 1 factorial, 2 factorial, 3 factorial, and so on. Suddenly, the rules you thought were fixed start to bend, and something new emerges: the factorial number system. Let's begin with the word factorial. It sounds complicated, but the idea is very simple. 1 factorial is just 1. 2 factorial means 1 times 2, which is 2. 3 factorial means 1 times 2 times 3, which is 6. 4 factorial is 1 times 2 times 3 times 4, which is 24. Factorials grow very, very fast. Now imagine building a number system where each digit isn't worth a power of 10 like in our normal counting, but instead each digit is worth 1 factorial, or 2 factorial, or 3 factorial, or 4 factorial, and so on. In normal counting, the rightmost place is worth 1, the next is worth 10, the next is worth 100. But here the first place is worth 1 factorial, the next is worth 2 factorial, the next is worth 3 factorial. It's like changing the rhythm of the universe's drumbeat. At first it feels confusing. How can you count this way? But actually it makes some things easier. For example, every whole number can be written in exactly one way using the factorial number system. That means there's no repeats, no overlaps, no messy, oh, this number could be written in 2 ways. It's neat, clean, and unique. That's very rare in math, and it's one reason mathematicians love it. Think of it like a puzzle game. You have slots: the 1 factorial slot, the 2 factorial slot, the 3 factorial slot, and so on. Each slot has rules for how high the digit can go. For example, in the 2 factorial slot, the digit can only be 0 or 1. In the 3 factorial slot, the digit can be 0, 1, or 2. In the 4 factorial slot, it can be 0, 1, 2, or 3. See the pattern? Each slot allows just enough digits to keep everything from overlapping. It's like perfectly stacking blocks so nothing ever spills over. One amazing use of this system is in ordering. Let's say you wanted to list out every possible order of a group of objects, like every possible way of arranging books on a shelf. That's what factorials naturally count. The factorial number system is perfect for this because it directly links to those arrangements. Each number in this system corresponds to one exact ordering. It's like nature designed it for the problem of shuffling things. But there's a strange beauty here too. Our world is built on habits. 10 fingers, so we made base 10. But the factorial number system asks us to step outside that habit, to see numbers not as something fixed but as something flexible. You realize that normal arithmetic is just one version of reality. There are many possible versions, and each tells a different story. Now pause and think about this. What if instead of tens, our ancestors had chosen factorials as the way to count? How different would our math look today? Would multiplication tables feel strange, or would they feel natural, the way base 10 does for us now? And this is the lesson hidden in the factorial number system. Numbers are not just tools, they are lenses. They shape the way we see patterns, order, and even possibility itself. By stepping into this world of factorials, we're reminded that even something as simple as counting can be reimagined. Take a moment to let that thought rest. The way we see numbers isn't absolute, it's chosen, and when we choose differently, whole new worlds of arithmetic open up, waiting quietly in the shadows.
Have you ever noticed how we build numbers on top of invisible scaffolding, like a house resting on its foundation? Normally, the foundation is a positive base, like base 10 for our everyday decimal system. 10 fingers, 10 digits, 10 as the anchor. But imagine, just for a moment, if that foundation wasn't positive. Imagine building numbers on top of a negative base. A strange, upside-down world where the very ground we stand on leans in the other direction. That is what negative base arithmetic gives us. Numbers built not from 10 or 2 or 3, but from -2, -3 or other negative foundations. At first it sounds impossible, almost like nonsense. But when you see how it works, it feels like a trick the universe was keeping secret all along. Think about the usual way we write numbers. In base 10, the digits sit in places that each represent powers of 10, ones, tens, hundreds, thousands, and so on. Every step to the left multiplies the place by 10. In base 2, it's the same idea, except each step multiplies by 2. But now, imagine base -2. Each step to the left multiplies by -2, not just 2. So instead of the places being 1, 2, 4, 8, 16, they become 1, -2, 4, -8, 16, -32, and so on. Suddenly, the simple pattern of place values becomes a dance of positives and negatives. Why is this interesting? Because now numbers don't need a negative sign in front of them. The very system itself can represent negatives automatically. For example, in base -2, the number written as 1101 doesn't mean what it would in binary. Instead of being 13, it represents -3, without needing a minus sign, just by where the digits land in those positive and negative places. It's like the system already knows how to balance itself, weaving back and forth between positive and negative as it climbs. Take a moment to reflect on that. We often think of the minus sign as a symbol we tack on when something is below 0. But in negative bases, the idea of minus isn't extra. It's baked into the very structure. The world of numbers flips upside down and in doing so erases the need for an explicit minus. It feels almost magical, like a secret alternate language numbers can speak when they get tired of ordinary rules. And here's what makes it even more mind-bending. You can represent every whole number, positive or negative, without ever writing a minus symbol. The digits themselves, sitting in their strange alternating positions, take care of everything. Positive bases gave us order. Negative bases give us balance. Of course, working with them isn't always smooth. Adding and subtracting can feel strange at first. Multiplying means carefully respecting those alternating signs. But the beauty is undeniable. With negative bases, the line between positive and negative dissolves into a single continuous fabric. No more this side of 0 and that side of 0. Just a flowing system where both are written naturally. And maybe that's the hidden lesson. Sometimes we think of opposites, like positive and negative, as separate forces locked in battle. But systems like negative base arithmetic remind us that opposites can live together in the same structure, balanced, self-contained, and whole. Numbers don't mind switching the foundation beneath their feet. They still stand, still make sense, still tell their story. And as we move forward deeper into stranger forms of arithmetic, we'll see this lesson again and again. Systems that look odd at first glance turn out to be mirrors, reflecting hidden truths about balance, symmetry, and possibility. Negative bases are only the beginning. Next, we'll step into the world where the base itself isn't just negative or positive, but something even stranger, complex. A base made not of real numbers at all, but of numbers with an imaginary part. Are you ready to imagine numbers built on a foundation of I? Have you ever thought about what it would mean to count using something that is not even a normal number? Not 2, not 10, not -2, but something even stranger like the square root of -1, the thing we call I. At first it sounds impossible. How could you ever build numbers in steps of I? And yet that is exactly what complex base arithmetic allows us to do. It invites us into a world where the very place values, the spots we normally think of as ones, tens, hundreds, are no longer simple, neat jumps of 10. Instead, they twist and turn into the world of complex numbers. Normally, when we write a number like 123, we know what each digit means. The 3 stands for 3 ones, the 2 stands for 2 tens, and the 1 stands for 100. The system is comfortable, predictable, and it works everywhere in daily life. But now imagine a system where instead of using 10 as the building block, we use I, the strange number that means the thing which, when multiplied by itself, gives -1.
This number I has fascinated mathematicians for hundreds of years. It feels unreal, almost magical, and yet it is solid enough to build real mathematics on. In a complex base system, we might choose I as the base, or even -1 plus I. That means every digit place doesn't just stretch numbers forward, it sends them sideways, or diagonally into the complex plane. A digit on the second place is not 10 times the first one. Instead, it could be I times the first one. This shifts the meaning of digits in ways that feel almost like walking in a maze where the hallways keep bending into new directions. What's incredible is that every number, yes, every single one, can still be written down in this system. You don't even need negative signs anymore. Because of the way I twist the place values, numbers that are negative in our usual base 10 appear naturally in the expansion of digits. In fact, in base -1 plus I, you don't even need minus symbols at all. The digits themselves take care of it. It's like a built-in magic trick hiding inside the arithmetic. Think for a moment about what this means. In our ordinary world, place value feels like a ladder, 1, 10, 100, 1000, up and up forever. But here in the world of complex bases, place value feels more like a spiral staircase. You're not just moving upward, you're winding around, circling into new positions, weaving between real and imaginary steps. Numbers are no longer just lines stretching to the left and right, they become points dancing across a plane. This system forces us to rethink the very idea of what numbers are. We're so used to thinking that digits must march forward in a line, neat and ordered. But here, order itself takes a new shape. Addition and subtraction still work, but the way digits carry or line up is unlike anything in base 10. Multiplication stretches in new directions too. It's like arithmetic in a hall of mirrors, where reflections still follow rules but in ways that trick the eye. Pause for a second and let that sink in. A base made of I means a whole new kind of counting, one that reaches beyond the line of numbers you first learned as a child. It pushes arithmetic into two dimensions, into a plane where numbers can move sideways as easily as forward. And what does this open up? For mathematicians, it means fresh ways to represent data, explore symmetry, or compress information. For the imagination, it means realizing that even the foundations we thought were unshakable, like the idea of place value, are more flexible than we ever guessed. Numbers aren't stuck in straight lines. They can spiral, they can twist, they can dance. Have you ever noticed how some numbers feel special, almost magical, as if they hold secrets hidden deep inside? Among all numbers, there is one that artists, architects, and even nature itself seem to love. The golden ratio. People usually call it phi. It's about 1.618, but more than its value, it's the way it shows up everywhere that makes it so mysterious. From the spirals of seashells to the shapes of galaxies, phi seems to whisper the language of beauty. But what if I told you we can actually build an entire number system using phi as the base? Not 2, not 10, but phi itself. This is called base phi arithmetic, and it bends the rules of numbers in ways that almost feel unreal. Let's start simple. You already know base 10, the numbers we use every day. 10 is our anchor, which means after 9 we carry 1 into the tens place and so on. Computers love base 2, which uses only zeros and ones. But phi is not a whole number, and that's where the magic begins. Imagine trying to build numbers not on a clean staircase like 2, 3, 4, but on a staircase that skips, stretches, and twists because phi itself is irrational. It never ends and never repeats when you write it out. It's like building a tower on a foundation that never lines up evenly, yet somehow the tower still stands tall and perfect. In base phi arithmetic, something very strange happens. You don't need to use two ones in a row. Why? Because phi has a special property. Phi squared is the same as phi plus 1. That means whenever you would normally have to carry over like in base 10 and base phi, you can rewrite it in a cleaner way. Two ones sitting next to each other are never allowed, because you can always replace them with a phi plus 1 somewhere else. It's like tidying up your room by folding everything neatly instead of letting socks scatter on the floor. Numbers in base phi always end up with this clean, simple look. But what does this actually feel like? Think of building blocks. In base 10, each block is a stack 10 times taller than the one before it. In base phi though, the blocks grow in a strange, uneven rhythm, phi times taller, but phi itself isn't neat. And yet when you put these blocks together, they always click into place without gaps. You can even represent whole numbers, fractions, and endless sequences, all without needing repeats like in decimal systems. That's part of why some people call base phi arithmetic elegant, even beautiful. It hides efficiency inside complexity. Take a moment to reflect on this. Numbers, which we often think of as rigid and cold, can actually behave like art. They can bend, stretch, and reorganize depending on the rules we choose. In base phi, the ordinary carrying process transforms into a dance where patterns balance themselves and where digits fall into harmony with one another. It almost feels like music written into arithmetic. And here's something even more surprising. Because phi shows up so often in nature, the spiral of sunflowers, the curve of hurricanes, using base phi to describe things can sometimes feel more natural than using base 10. It's as though the universe itself leans toward phi, and by working with it directly, we're speaking the same language as the world around us. Numbers no longer feel forced or artificial. They breathe and flow like waves or branches. But of course, this raises a question. If base phi works so beautifully, why don't we use it in everyday life? The answer is simple: convenience. Base 10 is easy for us because we have 10 fingers, and it's what we've always used. Base phi may be elegant, but it's trickier to compute, harder to teach, and less practical for things like grocery shopping. Still, for mathematicians and dreamers, base phi arithmetic remains a hidden treasure, a different way to see the world.
Have you ever thought about how we normally write numbers? We use the digits 0 through 9, stacking them in places like ones, tens, hundreds, and so on. It feels natural, almost automatic. But what if I told you there's another way? A way that doesn't use tens at all, but instead uses the famous Fibonacci numbers. Imagine writing every number not with 1, 10, 100, but with 1, 2, 3, 5, 8, 13, 21, and so on, where each number is the sum of the two before it. That's what's called the Zeckendorf Representation, and it changes the way we think about what numbers really are. Here's the strange part. In this system, every number can be written in exactly one way using Fibonacci numbers, as long as you never use two Fibonacci numbers that sit next to each other in the sequence. So for example, if you want to write the number 10, you don't say 8 plus 2 plus nothing else. Instead, you say 8 plus 2 and you're done. You can't sneak in a 5 and a 3 because those are next to each other in the Fibonacci list. This little rule keeps the whole system neat without overlap or confusion. Think about it like Lego blocks. Each Fibonacci number is a block of a very specific size. If you try to build a tower to reach a certain height, let's say 25, you'll grab the biggest block that doesn't go over 25, which would be 21. Now you have 4 left. To fill 4, you can't pick 3 and 2, because they're next to each other on the Fibonacci list. Instead, you grab 3, and then 1. And now you've built 25 with 21, 3, and 1. No other combination works under the rules. It's like a puzzle where there's always one right solution. Why does this matter? It reminds us that our usual base 10 system isn't the only game in town. Numbers aren't bound to just one kind of alphabet. They can be spelled out in many different languages of digits, and the Fibonacci language has a special beauty because it links ordinary counting with one of the most famous patterns in nature. Think of sunflowers, pine cones, shells, galaxies. All of them echo Fibonacci spirals. And here we are, using that same spiral's numbers to build our counting system. Take a moment to reflect on how wild that is. The numbers we see in flowers and seashells are the same ones that can build our arithmetic. It's as if nature already wrote a hidden number system into the world, and mathematicians simply uncovered it. And there's another twist. This representation makes certain problems in computer science easier. When computers are asked to compress information or search through patterns, sometimes Fibonacci-based numbering gives them shortcuts. It's like having a secret key that unlocks doors more smoothly than the regular base 10 key. So next time you think about the number 100, imagine writing it in Fibonacci blocks. Instead of 100, it becomes 89 plus 8 plus 3. It feels odd at first, but soon you see the elegance. Each number becomes a little story told in pieces of Fibonacci. And just when you begin to get used to this system, remember, it's not the only alternative base out there. There are number systems built from negatives, from fractions, even from the golden ratio itself. If Fibonacci can reshape arithmetic, what happens when we let other strange bases take over? Have you ever stared at something very tiny like an ant walking across the floor and thought, how small can small really get? You can zoom in with a magnifying glass, then a microscope, then an even stronger microscope. But is there an end? Does smallest really exist? Or can we keep going forever, breaking things into tinier and tinier pieces? Now think about something else. Big numbers. You can count 1, 2, 3, 100, 1,000, 1 million. But is there a biggest number? No matter what number you pick, you can always add one more. That means numbers go on forever in both directions, tinier and tinier on one side, and larger on the other. Hyperreal numbers live in this strange in-between world. They give us a way to talk about things that are infinitely small, smaller than anything we can normally write down, but not exactly zero. And they also let us speak about things that are infinitely large, bigger than anything we can ever count, but still not just infinity in the vague sense we usually say it. They are numbers that let us zoom into infinity itself with more precision. To see why this matters, think about calculus, the math of change. Calculus asks questions like, if I move a little, how fast am I going? Or if I add up an infinite number of tiny slices, what total do I get? Usually we use limits to handle these questions. Limits are like carefully stepping close to the edge of a cliff without falling off. You approach the value closer and closer, but never directly touch it. Hyperreal numbers change that. Instead of tiptoeing with limits, they give you actual numbers to hold in your hands, numbers that represent these infinitely tiny steps. Imagine a number called epsilon. Epsilon is not 0, but it's smaller than 1 divided by a trillion, smaller than 1 divided by a billion, smaller than anything you can think of.
and yet it's not nothing. If you add epsilon to 1, you get a number just a little larger than 1. If you multiply epsilon by 1,000,000,000, it might become noticeable. It's like having a shadow number that lives on the edge of 0 but never falls into it. On the other end, you can imagine an infinite giant number. Call it omega. Omega is bigger than any number you know, bigger than 1,000,000, 1,000,000,000, 1,000,000,000,000 all at once. But omega is not just a fuzzy infinity, it's a kind of number you can actually work with. For example, you can say omega plus 1, or omega minus 2. And strangely enough, even omega has its own tiny fractions. 1 divided by omega is one of those epsilon-sized numbers. The hyperreal system ties the infinitely small and the infinitely big together like opposite ends of the same rope. Take a moment to reflect on this. We live in a world where everything we see feels either large enough to hold or small enough to notice. But hidden beneath that, math whispers of realms where things exist smaller than dust, larger than galaxies, and yet still countable, still usable, still part of arithmetic. Hyperreal numbers give us a way to make sense of that. They are not just a dream, not just philosophy, they are a tool. With them, calculus becomes sharper. Instead of vague limits, we use actual infinitely small steps. Instead of hand-waving, we calculate with precision. It's like switching from a blurry lens to one that lets you see every grain of sand in perfect detail. And the implications? They remind us that infinity isn't some unreachable wall. It's a landscape we can explore step by step with numbers designed to live there. They show us that even nothing can have structure, and even everything can be measured.
Imagine you are sitting on the floor with blocks, and you keep stacking them higher and higher. At first it feels like you'll eventually run out of blocks, right? But now imagine that you have an endless box of blocks, so many that you could keep stacking forever, and the tower would never stop growing. This is what mathematicians call infinity. But here's the strange thing. Once you reach infinity, you can actually keep going further. Infinity is not the end, it is the beginning of a whole new kind of counting. And the way we do this is through something called ordinal arithmetic. Ordinals are numbers, but they don't measure size the way we usually think of numbers. They measure order. Think about lining up children in a row. The first child, the second child, the third child, that's the order. Now imagine lining up not just 10 or 100 children, but every child that could ever exist, going on forever. When you've finished counting all of them, you don't stop. Mathematicians say you've reached the first infinite position, which they call omega. And here's the fun part. You can still add one more child after omega, then another, then another. Infinity plus 1, infinity plus 2, infinity plus 100. It doesn't stop. This already feels strange, but it gets stranger. When we add with ordinary numbers, order doesn't matter. 3 plus 5 is the same as 5 plus 3. But when we add with ordinals, order changes everything. Infinity plus 1 is different from 1 plus infinity. Infinity plus 1 means you finish all the infinite children, and then you tack one more at the end. But 1 plus infinity means you start with one child, and then you have the endless row. That looks exactly the same as just infinity itself. The order reshapes the outcome. Multiplication is even wilder. Normally 3 times 5 is the same as 5 times 3. But with ordinals, infinity times 2 is different from 2 times infinity. Imagine lining up 2 full rows of infinite children, one after another. That's infinity times 2. It's like finishing one infinite row and then starting a second. But if you say 2 times infinity, you're just saying I'll make 2 children stand in front, and then an endless row behind them, which again collapses back to just infinity. Multiplication with infinity bends the rules we take for granted. And here's something even more mind-bending. There isn't just one infinity. Omega is the first infinity, but after that comes omega plus 1, omega times 2, omega squared, omega to the power of omega, and on and on. These are bigger and bigger infinities, each one towering above the last like mountains rising endlessly into the clouds. Ordinals let us see not just infinity, but whole landscapes of infinities stacked in impossible directions. Take a moment to let that settle in. We're used to numbers being fixed, simple and predictable. But ordinals show us a different world, where infinity can be counted, ordered, multiplied, and even built upon to create entirely new infinities. It's as if the universe of numbers stretches not just outward, but upward into new dimensions we rarely think about. And this leads to a strange thought. If infinity itself can be ordered, layered, and multiplied, then maybe forever isn't just one thing. Maybe there are countless kinds of forever, each one larger and more complex than the last. The mind struggles to picture it, but that's part of the beauty. Ordinals remind us that even the idea of endlessness has hidden depths. Have you ever thought about what it really means to count? We start small, 1, 2, 3. Then we climb higher, 10, 100, 1000. Eventually we say infinity, as if it's the end of the road. But here's the twist. Infinity is not just one thing. In math, there are different sizes of infinity, and this strange idea is called cardinal arithmetic. It sounds complicated, but at its heart, it's simply asking,
If infinity is endless, can one infinity actually be bigger than another? Let's take a simple picture. Imagine you have a line of people stretching forever. Person 1, person 2, person 3, and so on without end. That's one kind of infinity. We call it countable infinity, because even though it never ends, you could, in theory, keep counting one by one forever. Now let's imagine a line, but instead of people, it's every possible decimal number between 0 and 1. Numbers like 0.1, 0.5, 0.333, and infinitely many more. Numbers you couldn't possibly list no matter how hard you try. This is a bigger infinity. Suddenly, infinity isn't just big, it comes in layers, sizes, and shades. That's what cardinal arithmetic tries to explore. With normal numbers, arithmetic is straightforward. 2 plus 3 is 5. With infinity, things bend. If you add infinity to infinity, it is still infinity. If you multiply infinity by 2, it is still infinity. But when you start comparing different infinities, something strange happens. The infinity of the whole numbers is smaller than the infinity of the real numbers, the ones that include every decimal you can think of. And the infinity of all possible points in space is even bigger still. Infinity, it seems, refuses to be one size fits all. Here's an analogy. Imagine two hotels. The first is called the infinite hotel, with endless rooms, 1, 2, 3, and so on. Even if every room is full, the hotel can still make space for more guests, simply by moving each person from their room to the next higher room. Person in room 1 moves to room 2, room 2 moves to room 3, and so on. That's the magic of countable infinity. But the second hotel is stranger. Instead of numbered rooms, it has rooms labeled by decimals between 0 and 1. There are so many possible decimals, you can't even list them. No amount of shuffling could ever let you capture them all. This hotel holds a bigger infinity, one that countable infinity simply cannot match. The implications are mind-bending. It tells us that infinity isn't just a number sitting at the edge of mathematics. It's a whole universe of numbers, layered in hierarchies, some vast beyond comprehension. And when mathematicians compare these infinite sizes, adding them, multiplying them, exploring how they interact, they uncover patterns that seem both logical and impossible at the same time. Pause for a moment and reflect on this. Numbers which feel so simple and steady hide a reality where endless doesn't mean the same thing everywhere. One infinity can swallow another whole, just as an ocean dwarfs a lake, even though both feel boundless when you stand at the edge.
Have you ever stared at something very tiny, so tiny you could barely see it, and wondered, what if I could zoom in forever? Think of an ant crawling on the edge of a piece of paper. From far away, you see the paper is flat, but if you zoom in enough, the edge of the paper looks like cliffs and valleys, bumps and ridges. The closer you get, the more detail you see. And the question becomes, what happens if you never stop zooming in? This is the heart of what is called non-standard analysis. It is a way of doing arithmetic and calculus using numbers that are infinitely small and infinitely large. The normal math we learn in school tries to avoid this. Teachers say, don't divide by 0, don't talk about infinity as if it's a number, don't write down something smaller than anything else. But in non-standard analysis, we do exactly that. We allow numbers smaller than the tiniest fraction you can imagine, called infinitesimals. Here's one way to picture it. Imagine you're looking through a magical lens. To the naked eye, a line looks perfectly smooth. But when you hold the lens to it, you see that the line is not smooth at all. It has tiny wiggles, tiny bends, and tiny spaces that normal eyes cannot see. The lens shows you the hidden world of the line. Non-standard analysis is like that lens, letting mathematicians talk about details that ordinary arithmetic blurs away. Think of a number called epsilon. Epsilon is not 1, not a half, not even 1 over a million. It's smaller than any fraction you can name, yet it's not 0. It's the tiniest possible step. Now imagine numbers built from epsilon, like 1 plus epsilon, or 2 minus 3 epsilon. They are just like ordinary numbers, but with a little shadow attached, capturing what happens at the tiniest level. With these, you can describe things like how a curve bends or how a function changes, not just roughly, but exactly, at the smallest scale. And then there are the opposites, numbers so big that they're larger than anything you could count, bigger than a billion, bigger than a trillion, bigger than counting every grain of sand on every beach. These giant numbers stand shoulder to shoulder with the tiny epsilons, forming a new arithmetic, where you can calculate with both extremes at once. Why does this matter? Because the world itself is full of motion, change, and limits. Think of water flowing, planets orbiting, or a ball rolling down a hill. To describe these things, ordinary calculus uses limits, an idea that sneaks infinitesimals into the back door but never admits they exist. Non-standard analysis opens that door wide. It says, infinitesimals are real,
Infinite numbers are real. Let's use them honestly and clearly. Suddenly, calculus feels less like a trick and more like a natural story. But there is something even more beautiful here. This kind of arithmetic reminds us that the world is never as simple as it first seems. What looks smooth may hide endless detail. What looks empty may hold countless layers. And in this way, non-standard analysis is not just math, it's a philosophy about seeing the unseen. Take a moment to sit with this thought. Numbers can be infinitely small and infinitely large, and yet we can use them to measure, to calculate, to predict. Arithmetic becomes a language for both the tiniest whispers and the loudest echoes of the universe.
Have you ever tried to organize your toys, only to realize that no matter how neatly you line them up, you could always imagine more and more? That's what happens when we step into the strange world of infinite numbers. They don't just go on forever. They can also be arranged, stacked, and built into patterns. And one of the most careful ways to do this is called Cantor normal form. It sounds complicated, but the heart of it is simple. It's like giving infinity a neat and tidy filing system, so even the endless can be written down in order. Think of it this way. When we count ordinary numbers like 1, 2, 3, and so on, they line up nicely. 10 comes after 9, 100 comes after 99. Everything has its place. But when we step into ordinal numbers, the kind of numbers that don't just measure size but order, we get a whole new universe. Imagine saying not just I have 10 toys, but here's the order of my toys forever and beyond. You don't just stop at 10 or 100, you can go on endlessly and then start stacking new kinds of forevers on top of the first. Cantor normal form is like the instruction manual for stacking these infinities. It says don't just throw them around randomly, let's break them down into pieces, each one being a power of omega. Omega is just the mathematician's way of saying the first infinity. You can think of omega as the moment where counting never ends and then takes a new step forward. So Cantor normal form writes every ordinal as a sum of these omega powers, like neat building blocks. Instead of being lost in an ocean of infinity, you suddenly have islands, categories, and labels to hold on to. Here's an example in everyday words. Imagine a clock that doesn't just count hours, but keeps going forever. Once it finishes all its hours, it starts again. But this new round isn't the same as the first. It's stacked above it. And then after that, another round stacks above that. In Cantor normal form, you would say, this whole clock cycle is omega. 2 cycles is omega times 2. 100 cycles is omega times 100. And then you can even go beyond that to omega to the power of 2, which means not just repeating cycles, but a whole new dimension of endlessness. It feels strange, doesn't it? To not only count forever, but to build shapes and ladders out of forever. That's what makes Cantor normal form so powerful. It tells us that infinity isn't a messy tangle. It can be structured, layered, and arranged with precision, just like stacking books on a shelf. Why does this matter? Because infinity shows up in logic, in computer science, even in philosophy. If you want to prove things about order, or about processes that never end, you need a clear way to talk about infinity. Cantor normal form gives that clarity. It lets us say, here's exactly where this infinity stands compared to that one. Pause for a moment. Let your mind sit with that. Not only can infinity exist, but it can be written down, described, and structured. Infinity has rules. Infinity can be filed away like notes in a binder. And yet, even with this order, there's always more. No matter how many times we write down omega, omega squared, omega to the power of 1,000,000, there's always a bigger one waiting. Cantor normal form never ends. It just keeps letting us climb higher into the endless tower of numbers. So when you think of infinity, don't picture chaos. Picture shelves, ladders, and neat rows that stretch further than your eyes can see. That's Cantor's gift. Infinity, structured and calm, like a library with no end. Have you ever been told that infinity is not really a number, but more of an idea? In most of the math we learn as children, infinity feels like a wall we cannot pass. We can keep counting 10, 100, 1,000, 1,000,000, but infinity always stays far away, untouchable. But imagine if, instead of treating infinity as something outside of math, we actually invited it inside, gave it a seat at the table, and said, you are a number now, and we can calculate with you. That is what projective arithmetic does. It stretches ordinary numbers by adding new kinds of numbers, points at infinity. Think of the number line you know,
a straight path with 0 in the middle, stretching left toward negative numbers and right toward positive numbers. Now imagine bending that line into a circle. Suddenly the far left and the far right are no longer endlessly apart, they meet. And where they meet, that's where infinity lives. It's like the world is round. If you keep walking east long enough, you don't fall off an edge. You arrive back where you started. In projective arithmetic, infinity is not a mysterious cliff, but simply another place on the loop. Why is this important? Because it allows us to work with problems that would normally break under ordinary rules. For example, in normal arithmetic, dividing by 0 is impossible. It makes calculators freeze and teachers frown. But in projective arithmetic, dividing by 0 doesn't have to be meaningless. Instead, the answer can be infinity, that new point we added. It's not that the problem disappears, it's that the system grows bigger so it can handle it. This is similar to how cities expand. Imagine a small town with only a few streets. At first, everything fits neatly, but then new buildings appear, new roads stretch out, and the old map no longer works. Instead of saying this road goes nowhere, you redraw the map so that road connects to something new. That's what projective arithmetic does with numbers. It redraws the map of arithmetic so infinity has a home. Now here's where it gets even more surprising. Once infinity is added, it behaves like any other number, but with its own quirks. For example, adding any normal number to infinity still gives infinity. Multiplying infinity by anything but 0 also gives infinity. It's as if infinity swallows numbers whole, always staying the same, no matter what it eats. But infinity can also appear in fractions. If you take 1 divided by a very, very tiny number, the result grows bigger and bigger until it becomes infinity. Projective arithmetic allows that story to have an ending. The number simply reaches the infinity point. Take a moment to reflect on that. Instead of being an unreachable horizon, infinity becomes part of the landscape. We can walk to it, touch it, and even use it in calculations. Doesn't that change how you feel about math? But there's also something quietly mysterious here. When you add infinity to your number system, you're not just solving problems, you're also changing the nature of numbers themselves. Suddenly, numbers are no longer only about size or counting. They are about structure, shape, and how we choose to draw the boundaries of reality. By bending the line of numbers into a circle, we admit that infinity might not be out there, but right here, folded into the system we already use. This idea is not just abstract. Projective arithmetic shows up in geometry, physics, and even computer graphics. Whenever we deal with perspectives, vanishing points, or objects that stretch into the horizon, projective arithmetic is quietly working behind the scenes. Those lines that seem to meet at infinity on a drawing, that's not magic. It's numbers doing their work in a projective world. And so infinity becomes less frightening and more familiar. It is no longer a wall but a doorway. A doorway to new kinds of arithmetic, where the impossible becomes possible simply because we dared to imagine a number system larger than the one we were given.
Imagine you have a big cake. You want to cut it in a way that separates the small slices from the big slices. One side of the cut has all the smaller pieces and the other side has all the bigger pieces. That cut, that dividing line, is kind of like what a mathematician named Richard Dedekind thought about with numbers. He wondered, what if we could take all the fractions, the ones like 1/2, 2/3, or 5/4, and slice them into two neat piles, one side holding all the smaller fractions, and the other side holding all the bigger ones. At first this might sound simple, but here's the strange part. Sometimes that cut doesn't land on any fraction at all. Take the square root of 2, for example. You can try to find it using fractions. One fraction says 1.4, another says 1.41, another says 1.414. You can keep guessing closer and closer, but no fraction ever lands perfectly on the square root of 2. It's a number that hides between the cracks. Dedekind realized even if no fraction exactly touches it, the cut itself tells us the number is there. That invisible spot where the two piles of fractions meet, that's how you can define a real number. So Dedekind cuts are like drawing a line between too small and too big. Everything below the line is one pile of fractions, and everything above the line is another pile. The line itself is the real number. Sometimes that number is a fraction we already know, like 1/2. But sometimes it's a mysterious number we couldn't quite pin down before, like the square root of 2, or pi. This idea is special because it showed us a way to build the real numbers step by step, out of nothing more than fractions. Instead of saying, well, the square root of 2 just exists, trust me, Dedekind gave us a recipe. Take fractions, split them into two piles, and the border between them is the number you're looking for. Take a moment to reflect on that. Numbers like pi,
which feel magical and impossible, can be caught not by writing them down directly, but by cutting reality into pieces over and over until you've surrounded the number with fractions that never quite touch it. Now think about the implications. It means real numbers aren't some mysterious gift from the heavens. They're carefully carved out of ordinary fractions by this slicing method. It's like saying every ocean is really just a lot of tiny drops of water put together. Every continuous line you see in the world is actually built from tiny jumps, tiny separations, tiny cuts. This is also unsettling in a way. It tells us infinity is always hiding there. Because between any two fractions, no matter how close, there's always another fraction. You can never stop slicing. The cut doesn't just divide, it whispers that there's no end to dividing. Imagine you're really thirsty and someone gives you a glass of juice, but instead of pouring the whole drink at once, they say, "Wait, let's do something fun. First I'll give you one glass, then I'll give you another, but this time it's 1/2, then another, but it's 1/3, and then 1/4, and so on." You'd start to realize something strange. The drink doesn't come in simple, neat amounts. It comes in layers, like a staircase of smaller and smaller pieces. This is the world of continued fractions. Instead of writing a number in the usual way like 3.14 for pi, you write it as something that goes on and on with fractions stacked inside fractions. Picture this: 1 plus 1/2 plus 1/3. But instead of stopping, you keep building deeper and deeper. It's like a nesting doll of numbers, where each doll hides another inside, and that doll hides another, and it never really ends. Why would anyone want to write numbers this way? Well, here's the secret. Continued fractions capture numbers in their purest rhythm. If you've ever seen waves hitting a shore, each wave feels like it's chasing the last one, almost repeating but not quite. Continued fractions capture that same kind of hidden heartbeat inside numbers. Some numbers, like pi, look random and messy when you write them with decimals. But when you write them as continued fractions, suddenly you see patterns, simple steps that explain why these numbers feel infinite, but not chaotic. Take the number called the golden ratio. In decimals, it's long and clumsy, 1.618, and so on forever. But as a continued fraction, it's stunningly simple, 1 plus 1/1, plus 1/1, plus 1/1, repeated endlessly. It's like looking at a messy painting, and then suddenly finding a perfect spiral hidden inside it. That's the magic of this arithmetic. It takes what looks impossible and turns it into something beautifully structured. Now here's where it bends your mind. Normally when you think of fractions, you imagine cutting things smaller, half a cake, a third of a pie, a quarter of a pizza. But with continued fractions, you're not just cutting, you're building ladders. Every step higher is made of the previous step's fraction. It's like saying, this fraction doesn't stop at one cut, it grows into another cut, and that cut grows into another. Suddenly infinity isn't just endless, it's layered, step by step, like an infinite staircase. And what happens if you try to calculate with these fractions? Something curious. The closer you climb this ladder, the more accurate you get to the real number. Each step, each layer, is like zooming in closer to truth. You never quite touch the exact number, because infinity always stretches ahead, but you get so close that the difference feels almost invisible. It's as if numbers are teasing you. You'll never catch me, but you'll always almost catch me. Think about what that means. Numbers we thought were untouchable, like pi or e, suddenly give up their secrets when seen through this lens. It's not magic, it's structure, a hidden rhythm that waits only for the right key to unlock it. So the next time someone says a number goes on forever, like pi, you'll know the truth. It doesn't just wander randomly. Deep down, it dances to the beat of fractions stacked forever, one inside another. Imagine for a moment that you live in a world where the rules of math have been rewritten. A world where adding two numbers doesn't mean putting them together to get something bigger, but instead means choosing whichever number is smaller. And multiplying two numbers doesn't mean repeated addition, but simply adding them the usual way. This strange but beautiful system is called tropical arithmetic. It sounds like a game you'd play on the beach with seashells, but in reality, it's a very deep idea used by mathematicians to solve some of the hardest puzzles in geometry and computer science. Let's begin with the first strange rule. In tropical arithmetic, when you say add, you really mean take the smaller one. So if I ask, what is 2 plus 5, you don't say 7, you say 2, because 2 is smaller. That feels upside down, doesn't it? Normally addition makes numbers bigger, but here it shrinks them down to the smallest choice. It's like two people racing to a finish line. In regular math, both of their times would somehow get combined. But in tropical arithmetic, only the fastest runner matters. The smallest number always wins. Now let's look at multiplication in this strange world. In tropical arithmetic, multiplication isn't about groups of groups anymore. Instead, it becomes regular addition. So if I say, what is 3 times 4? You don't count up 3 4 times to get 12. Instead, you just add them the old-fashioned way, 3 plus 4, which makes 7. Surprising, right? Multiplication has been softened into something simpler. Why would anyone bother doing math like this? At first it feels like nonsense, like flipping rules just for the fun of it. But tropical arithmetic has an amazing secret. It makes very complicated shapes and patterns much easier to study. Imagine you're looking at a tangled knot. In normal math it might take forever to untangle. But in tropical arithmetic, the knot straightens out into something made of lines and corners, much easier to see and understand. This strange system shows up in places you wouldn't expect. For example, if you're trying to figure out the fastest way to get from your house to school, and there are many different paths, you don't care about all the extra details. You just care about the smallest time it takes. That's exactly how tropical arithmetic thinks, always choosing the minimum. In fact, it's used in optimization problems, which are all about finding the best or smallest way to do something. There's also something very calming about this. Usually, math feels like it pushes you higher and higher, numbers getting larger, sums piling up, multiplications exploding into huge results. But tropical arithmetic moves the other way. It takes the chaos and reduces it, slowing everything down, focusing only on what's smallest, what's simplest. Take a moment to reflect on that. Sometimes the smallest step, the quietest answer, is the most important one. And yet this backward-feeling arithmetic challenges us to ask, what is math, really? Is it fixed, unchangeable, carved into the universe? Or is it something we can bend, reshape, and reinterpret like clay in our hands? Tropical arithmetic proves that by flipping just a couple of rules, we create an entirely new world with its own beauty, its own order, its own mysteries.
Imagine if numbers were not sharp, exact things, but instead soft, like a cloud. Normally, when we say a number, we expect it to be exact. 7 means 7, nothing more, nothing less. But fuzzy numbers are different. They allow us to say something like, this is about 7, but it could also be a little less or a little more. Instead of being a hard point, the number becomes more like a range with shades of possibility. Think about temperature. If you ask, is it hot outside? One person might say yes, another might say no. For someone, 20 degrees feels warm, but for someone else, it feels chilly. The truth of the statement, it's hot, isn't just yes or no, it's somewhere in between. Fuzzy numbers let us handle this in math. They don't say, the answer is exactly this. They say, the answer is around here with a certain degree of truth. You've probably noticed how the real world almost never gives us perfect numbers. If you're baking cookies, the recipe might say 200 grams of sugar, but you don't usually measure exactly 200. Maybe you pour 199, maybe 21. It doesn't ruin the cookies. Why? Because the number didn't need to be sharp. It had wiggle room. Fuzzy numbers capture that wiggle room. They don't trap us in the illusion of perfect accuracy when we don't actually have it. To make this idea clearer, imagine you ask someone, how tall is that tree? They say, about 10 meters. That word about is doing fuzzy arithmetic. It means it could be 9.8 or 10.2, and all of those are included in the idea of 10. Instead of being trapped by a single exact number, fuzzy numbers spread out softly, like a shadow. The amazing thing is how fuzzy numbers change the way we calculate. If we add fuzzy numbers, we don't just add two exact values, we add ranges of possibility. If you say, I'll need about 3 apples and about 4 apples, fuzzy arithmetic says, okay, then you'll need about 7 apples, but maybe 6, maybe 8. The fuzziness carries through the math, just like real-life uncertainty carries through decisions. Why is this powerful? Because our world is full of uncertainty. Machines break down, measurements are never exact, people's feelings can't be neatly boxed into ones and zeros. Normal arithmetic demands sharp answers, yes or no, exactly this, or exactly that. But fuzzy arithmetic makes space for uncertainty, just as the real world demands. It says, things don't have to be exact to still be useful, understandable, and even predictable. Take a moment to reflect on this. How often do you give answers in life that are not exact, but still meaningful? You say, I'll be there in about 10 minutes. You say dinner costs around $20.
You say, "It feels kind of warm today." Each of these is fuzzy arithmetic happening in your daily life, even if you didn't know it had a name. And here's a curious thought. Fuzzy numbers also change how we think about truth itself. In classical math, something is either true or false, black or white, but fuzzy logic says truth can be partial, something can be half true, or 70% true. It sounds strange, but in fact it's much closer to how we live. Is the glass half empty or half full? Both answers are somewhat true. Fuzzy numbers give us the language to handle this kind of middle ground without forcing us into rigid boxes.
Have you ever noticed how we always expect numbers to be exact? When we say the answer is 2, we mean exactly 2. Not a little more, not a little less, just 2. But the real world doesn't always work like that. Think of measuring the length of your desk with a ruler. You may say it's 1 meter long. But is it really exactly 1 meter? Or is it maybe 1 meter and a tiny hair more, or a tiny hair less? We don't know, because our tools aren't perfect. Numbers in life often come with fuzziness. This is where interval arithmetic steps in. Instead of saying a number is exactly 1, we say it could be anywhere between 0.9 and 1.1. We don't pick just one spot. We give a whole range. It's like saying, I'm not certain where the truth lies, but I know it's inside this box. That's what interval arithmetic is about, working with boxes of numbers instead of single points. Let's picture this. Imagine you're baking cookies. The recipe says bake for 10 minutes. But ovens aren't perfect. Maybe your oven runs a little hot, maybe it runs a little cool. So instead of being sure the right time is 10 minutes exactly, you know the sweet spot is probably somewhere between 9 and 11 minutes. Interval arithmetic captures that idea. It allows us to say, the answer is somewhere in here, and then carry that uncertainty forward through all the calculations. Think of adding 2 ranges. If one ingredient weighs between 4 and 6 grams, and another weighs between 3 and 5 grams, then together they weigh somewhere between 7 and 11 grams. You don't pick just one answer, you honor the uncertainty. It feels different from usual arithmetic because we're not hunting for precision, we're protecting ourselves against mistakes. Now pause and reflect on this for a moment. Isn't it strange that we usually pretend numbers are exact, when in reality most of life's numbers are not? Measurements are never perfect. Predictions are never exact. The world breathes in ranges, not sharp edges. Interval arithmetic is simply math admitting that truth. The implications are huge. Engineers designing bridges, scientists tracking planets, doctors estimating medicine doses, all rely on numbers. If they assume exactness when there is none, small errors can snowball into disasters. But if they use intervals, they keep the uncertainty visible. The bridge is safe across all likely scenarios. The medicine works even if measurements are slightly off. The prediction remains trustworthy. But there's also a philosophical twist. Interval arithmetic whispers to us, maybe truth itself isn't always sharp. Maybe what we call exact is just an illusion. Our world might be made of ranges, shadows where certainty hides. Doesn't that make you rethink how we approach problems? And then comes the truly mind-bending part. Imagine multiplying ranges, or dividing them. The uncertainty spreads, grows, shifts in unexpected ways. One tiny wiggle at the start can ripple outward until the final range is much wider than we thought. It's like planting a seed of doubt, and watching it blossom into a forest of possibilities. So as you drift with this thought, let it sink in. Interval arithmetic is not about weakness, but honesty. It admits that life is messy, and it builds strength from that messiness. Instead of pretending everything is sharp, it teaches us to carry uncertainty with grace. Have you ever noticed how sometimes when people try to predict the future, they give a number that sounds precise, but deep down, everyone knows it's not exact? Like when a weather reporter says it will rain tomorrow with 70% chance, what does that really mean? It doesn't mean rain is certain, and it doesn't mean it won't happen. It means the truth is hiding inside a kind of range, and that range is carrying uncertainty with it. But here's the problem. Most of the time, when people try to do math with these ranges, they treat each range like it's independent, floating all alone, and that's where mistakes creep in. This is exactly where something called affine arithmetic steps in. It's like interval arithmetic but smarter, because it remembers the relationships between the numbers instead of forgetting them. Let's make it very simple. Imagine you are drawing a picture, and your pencil line shakes a little because your hand isn't perfectly steady. If I told you the line could go anywhere between 1 and 3 millimeters wide, you'd have a range.
But now imagine every other line you draw is connected to that same shaky hand. If your hand shakes more one moment, it shakes more on all the lines at the same time. The usual way of working with ranges would forget this connection. It would pretend each line's shakiness is random and separate, but affine arithmetic says, no wait, these wobbles are related. They move together. And because it remembers this, the ranges it gives are much tighter, much closer to the truth. Think of affine arithmetic like a chef tasting soup. If you just list possible ranges for each ingredient separately, salt between 1 and 2 spoons, pepper between 0 and 1 spoon, water between 2 and 4 cups, you might think the final taste could be anything between bland and too salty to drink. But if you remember that the chef adjusts these ingredients together, less salt when there's less water, more pepper when there's more salt, the possible flavors shrink to a smaller, more realistic band. Affine arithmetic is basically math that works like that smart chef. It adjusts ranges by noticing the dependencies. And here's where it gets even more interesting. When computers simulate the real world, like weather systems, space travel, or even the bending of a bridge, they deal with millions of numbers that all have small uncertainties. If you only used ordinary interval arithmetic, those uncertainties would balloon out of control, leaving you with results so wide they're almost useless. Affine arithmetic calms that chaos. It gives numbers that aren't exact, but they're precise enough to trust. You know the answer isn't a single sharp point, but a narrow band that reflects reality better. Take a moment to reflect on that. We live in a world where certainty is rare. Predictions are always wrapped in some fog of doubt. Affine arithmetic is like a lantern in that fog. It doesn't remove the uncertainty, but it makes sure we see the shape of it clearly, instead of exaggerating it into something monstrous. So next time you hear a forecast, or you see a computer model of the future, remember, behind those numbers may be a quiet method like affine arithmetic, holding the strings together, keeping the ranges honest, and making sure uncertainty doesn't grow wilder than it really is. Imagine you're rolling a dice. Sometimes you get a 2, sometimes you get a 5, sometimes a 6. You never really know what's coming until it happens. But what if I told you there's a way of doing arithmetic where numbers themselves behave a little like dice, uncertain, carrying probabilities inside them? This is what we call stochastic arithmetic. It's like arithmetic with a built-in whisper of chance. Think about how you usually treat numbers. 2 plus 2 is always 4. Always. There's no doubt about it. But what if instead of just 2, you had a number that is usually 2 but sometimes 2.1, or maybe 1.9, depending on how the wind blows? Suddenly, adding those kinds of numbers is not so certain anymore. Instead of one fixed answer, you get a cloud of possible answers, with some being more likely than others. Why would anyone want numbers that are so uncertain? At first it sounds frustrating. We like certainty. We like that 4 will always be 4, but the world around us doesn't actually behave in perfectly clean numbers. Imagine measuring the length of your desk with a ruler. Maybe you think it's exactly 1 meter, but what if your eyes are slightly off, or the ruler is bent, or the desk swells a little because of the weather? The true length isn't just 1 meter, it's about 1 meter, give or take a few millimeters. That give or take is uncertainty, and stochastic arithmetic embraces it. In this system, every number is not just a number, it's a little probability cloud. You might say this number is most likely around 3, but it could lean toward 2.9 or 3.1. Now, when you add two such numbers together, you don't get a sharp single answer. You get another probability cloud telling you the result is most likely around 6, but it could drift a little higher or lower. Pause for a moment and think about how strange this feels. We grow up with the idea that numbers are exact, hard, unshakable truths. But here, numbers breathe. They wiggle. They admit they aren't perfect. And in a way, that makes them more honest. Because isn't real life full of wiggles? One of the most important uses of stochastic arithmetic is in computers. You might imagine that computers always calculate with perfect accuracy, but the truth is they often don't. Rounding errors, tiny mistakes, and small imprecisions pile up when doing millions of calculations. Instead of pretending those errors don't exist, stochastic arithmetic says, let's model them, let's make them part of the numbers themselves. That way, when the final answer comes out, we know not only the result, but also how uncertain it might be. It's almost like numbers are confessing their secrets. I am not exactly 7, a number might say. I am 7 plus or minus a little bit, with this likelihood attached to me. And when you combine many such numbers, you don't just get a total, you get a story about how reliable that total is. What's beautiful here is how this reshapes the way we think about truth in arithmetic. Instead of a single rigid answer, we get a spectrum of possibilities. And that spectrum is often closer to reality than the illusion of exactness we're used to.
Imagine you are trying to guess how many candies are inside a big glass jar. You can't see inside clearly, but you can shake it, listen, and peek through tiny gaps. You might say, I think there are around 100, but then you shake it again and say, maybe 95. And then later you try another guess. Maybe it's 110. Each time you are close, but never exactly certain. This is the spirit of something called Monte Carlo arithmetic. It's a way of doing math where instead of saying one exact answer, we say, let's try many guesses and see what the pattern tells us. Normally, arithmetic feels like a strict set of rules. 2 plus 2 is always 4. 10 times 10 is always 100. But what if we lived in a world where numbers themselves wiggled a little, where every time we calculated, the answer could shift, sometimes a bit higher, sometimes a bit lower? That's what Monte Carlo arithmetic imagines. It adds a touch of randomness to every calculation, not because we want chaos, but because it helps us understand uncertainty. Think of it like throwing dice. If you want to know what number will come up, you can't be sure before you roll. But if you roll again and again, you can notice the average. You might say, most of the time the dice give me around 3 or 4. That's not a single answer, it's a story told by many little chances. Monte Carlo arithmetic works the same way. Instead of trusting one calculation, it asks, what if we do this again, and again, and again, with a little bit of randomness each time? Why would anyone want to do that? Because in the real world, numbers are not always perfect. Computers, for example, don't hold every decimal place forever. They round numbers, they cut off tiny parts, and they make little mistakes. Usually we ignore these errors, but sometimes they build up and twist the result in surprising ways. Monte Carlo arithmetic says, let's stop pretending numbers are always exact. Let's embrace the fact that they are a bit fuzzy and use randomness to see how far off things might drift. Take weather forecasting. When meteorologists try to guess if it will rain tomorrow, they can't just crunch numbers once and be done. They run many simulations, each with slightly different starting points. Some say sunshine, some say rain, some say thunderstorms. By looking at all of them together, they can tell us there's a 70% chance of rain. That's Monte Carlo thinking, using many random tries to understand the bigger picture. Now pause and let that sink in. We are so used to math being exact, sharp, and perfect. But here is a system that says, no, math can also be like clouds, shifting, changing, uncertain, but still deeply meaningful. It shows us that randomness is not the enemy of truth. Sometimes, randomness helps us get closer to the truth than rigid certainty ever could. And maybe that's a lesson for life too. We often want things to be precise, our plans, our choices, our futures. But real life works more like Monte Carlo arithmetic. There's always some randomness, some uncertainty, some guesswork. And yet if we step back and look at the bigger picture, we can see patterns, we can find meaning, and we can make peace with the fuzziness. Imagine for a moment that every number you use in life was a little blurry. Not broken, not wrong, just softened around the edges. Like when you look at a light through fog, it's still there, but it doesn't have hard borders anymore. That's what soft arithmetic is all about. It's the world of numbers when they don't have to be exact, when being close enough is not only acceptable, but useful. Now, why would anyone ever want blurry numbers? Isn't math supposed to be sharp, clean, and exact? The answer lies in how the modern world actually works. Computers, robots, and especially artificial intelligence live in a reality that isn't crisp. They see the world through cameras, sensors, microphones, and signals. And all of these things are noisy, imperfect, and uncertain. If you give them sharp numbers when the world itself is messy, they end up making mistakes. But if you let the numbers themselves be soft, they can adapt, bend, and still work in situations where exactness would completely fail. Think about how your eyes see. When you're in bright daylight, the edges of objects seem clear. But in twilight, when the sun dips low, the world blurs. Your brain doesn't shut down just because it can't see perfectly. Instead, it adjusts, fills in the blanks, and gives you a good enough picture so you can still walk, run, or find your way home. That's soft arithmetic in spirit. Numbers that allow machines to move forward even when the picture isn't crystal clear. Here's a simple way to think about it. In regular math, 2 plus 2 is always exactly 4. In soft arithmetic, 2 plus 2 might still be 4, but it might also carry a whisper saying maybe a little more, maybe a little less. The number isn't a single dot anymore. It's like a cloud or a cushion, something that can stretch without breaking. And that stretchiness makes it powerful,
because the real world is not rigid either. Now here's the mind-bending part. When machines use soft arithmetic, they can reason like us. We don't always need precision. When you say, "I'll be there in 5 minutes," you don't mean exactly 5 minutes down to the last second. You mean roughly 5 minutes, give or take. If someone arrives after 6 minutes, you don't accuse them of breaking math. You accept the fuzziness. That's human. And soft arithmetic teaches machines to think in a similar way, to live comfortably with about right instead of demanding exactly right. But this blurring comes with strange consequences. In normal math, you can always trust multiplication or addition to behave predictably. In soft arithmetic, sometimes adding two soft numbers together doesn't give one exact result, but a range of possibilities. Like saying this apple is about 1 pound and that apple is about 1 pound. Together they're about 2 pounds, but could actually be 1.8 or 2.2. The softness doesn't destroy the truth, it just widens it. Why does this matter? Because artificial intelligence, those systems that drive cars, recognize faces, translate languages, lives in a world where perfect answers rarely exist. A self-driving car doesn't know with certainty if the object ahead is a shadow, a person, or a dog. Instead, it assigns probabilities. It thinks in blurred numbers. It reasons with softness. Take a moment to reflect on this. The very thing we were taught to avoid in school, being vague with numbers, is the very thing that gives machines the flexibility to act wisely in uncertain conditions. Clarity can be brittle. Softness can be resilient. Have you ever noticed how slow people can be when they add numbers by hand? You write one number on top of another, you add the digits, and if the sum is too big, you have to carry over to the next column. It's not hard, but it takes time, and you always have to remember where that little carried number goes. Now imagine a machine, a computer chip, doing this not once or twice, but billions of times every single second. Suddenly, carrying feels like a problem. That tiny delay in passing numbers from one column to the next again and again would be enough to make even the fastest machine stumble. And so, computers needed a trick. That trick is called carry-save arithmetic. The name sounds complicated, but the idea is surprisingly simple. It's like saying, what if we don't carry right now? What if we save it for later? Instead of slowing everything down every single time a carry shows up, carry-save arithmetic says, let's just keep track of the carries separately, we'll deal with them in the end. This way the machine can keep adding without pausing, without waiting, without getting stuck in the slow little dance of moving digits over. Picture it like this. You're in a classroom, and the teacher asks everyone to line up in rows of 10. Normally, if a row has 11 kids, one has to leave and go to the next row immediately. That's the carry step. But in carry-save arithmetic, nobody leaves right away. You just mark down that one extra kid is waiting to move, and the rows keep filling up. At the end, once everyone's in place, you move the extras all at once, much faster, much smoother, and no interruptions. This might sound small, but inside a computer chip, speed is everything. Think about multiplying two numbers. Multiplication is really just a huge pile of additions stacked on top of each other. If every single one of those required carrying immediately, you'd end up with a terrible traffic jam. But if you can postpone all those carries until the very end, you can blast through the calculation like a race car, only slowing down once. That's why carry-save arithmetic is like a secret engine hidden under the hood of your computer, making it far faster than it would otherwise be. Now, what's fascinating here is the lesson it gives us. We tend to think that being precise right away is always better. Get the answer now. Don't leave loose ends. Fix it immediately. But carry-save arithmetic whispers something different. Sometimes the best way to move quickly is to leave things unfinished for a while. Let the details wait. Don't stop progress just because of a tiny roadblock. Handle the little pieces later, when you're ready. Take a moment to reflect on that. How often in life do we slow ourselves down because we're obsessed with carrying every extra digit right away? Maybe like the computer, we'd go faster if we let some of those things wait until the end. Carry-save arithmetic doesn't just show us a smarter way for machines to add, it also nudges us to think differently about time, effort, and focus. Don't waste energy fixing every bump the second it shows up. Keep moving, stay in flow, and circle back later when it really matters. And just like a computer chip racing through billions of calculations, you might find yourself finishing faster than you ever imagined. Have you ever noticed how much of our math depends on carrying? Think back to when you first learned to add numbers. You add 7 plus 6, you get 13, and what do? You keep the 3, and you carry the 1 over to the next column. That little action, which feels so normal, is like the hidden glue holding our whole number system together. But what if I told you there are kinds of arithmetic where carrying simply doesn't exist at all, where addition works, but the rule of carrying vanishes? Strange as it sounds, this is not a mistake, it's an entirely different way of thinking about numbers. It's called carry-free addition. To understand it, imagine a world where every digit lives in its own little bubble. Usually when we add, digits talk to their neighbors. If something gets too big, like 9 plus 9 turning into 18, we pass that extra over to the next digit. That's carrying. But in carry-free addition, digits don't talk. They don't hand off extra pieces. Each one just stays put, no matter how large or small the sum becomes. It's as if the digits are living on islands, completely independent. At first, this feels wrong, almost broken. After all, we've been trained since childhood that carrying is essential. But when you remove it, something fascinating happens. Suddenly, the arithmetic looks lighter, faster, and easier for machines. For example, computers sometimes use this method because it lets them add huge numbers without stopping to pass carries along. Instead of one long chain of waiting, every digit adds at once. No delays, no bottlenecks, just parallel movement. Picture two children adding with blocks. Normally, if they stack too many blocks in one pile, they are told pass the extra to the next pile. That's carrying. But in carry-free addition, they're told don't worry about passing. Just let the pile be as tall as it wants. Each pile grows without interfering with the others. The answer isn't the same as in normal arithmetic, but it's consistent, and it follows its own rules. Now, here's where the mind-bending part comes in. By breaking free of carrying, we also break free of certain limitations. Operations can be done much faster. Entire systems of error correction in computers rely on this idea, because carry-free addition avoids mistakes that can spread from one digit to another. It's like having walls between rooms. If one room gets messy, it doesn't spill into the next. But what about the meaning of the numbers? If we can add without carrying, does that mean our normal numbers are only one version of the truth? Could it be that numbers aren't absolute, but shaped by the rules we choose? Carry-free arithmetic shows us that math is not just about one rigid system. It's about possibilities. Change the rules, and a new world opens. Take a moment to think about that. We often assume there's only one correct way to count, to add, to measure. But maybe that's only because we grew up with it. Carry-free addition is proof that numbers are flexible, that they can behave in ways that feel alien yet are perfectly logical. Imagine you live in a world where numbers don't always play by the same rules you learned in school. You're used to the normal kind of arithmetic, right? Add, subtract, multiply, divide. 2 plus 3 is always 5, no matter where you go. But what if there were other universes of numbers where the rules look the same on the surface? There's still addition and multiplication, but deep down things behave differently. That's the idea of ring arithmetic. A ring is not a shiny circle you wear on your finger. It's a whole new world where numbers live together, following rules that are familiar but also strange. Think of it like this. Imagine you're playing with Lego bricks. You know the basics, you can snap pieces together and pull them apart. But suppose in one world of Lego, every time you put two red bricks together, they magically turn blue. In another world, stacking a tall tower makes the bottom piece disappear. The rules are still about snapping bricks, but the outcomes are surprising. That's what a ring does. It sets up a space where you can still add and multiply, but the results don't always look the way you'd expect. Why is this fascinating? Because it tells us there's not just one way to do arithmetic. There are infinite possible worlds where numbers can be arranged with new rules. A ring is like a sandbox where mathematicians can say, what if we only used whole numbers? What if we used remainders after dividing? What if we used polynomials, or even matrices? Each of those choices builds a different ring. Here's a simple picture. Imagine the normal numbers you count with, like 0, 1, 2, 3. That's one kind of ring, very familiar. Now shrink the world down and say we only care about remainders after dividing by 5. Suddenly numbers wrap around. 2 plus 4 doesn't make 6 anymore, it makes 1. Because 6 leaves a remainder of 1 when divided by 5. In this ring, the rules still work. You can add, you can multiply, and it's consistent. But it's not the same as the ordinary numbers you learned in school. The magic of rings is that they help us explore arithmetic in almost any shape we want. Some rings are very tidy, like neat little gardens where everything grows in order. Others are wild forests where strange plants sprout up, like numbers that can't be divided, or rules where multiplication twists around in surprising ways. Take a moment to reflect on this. What feels natural to us, 2 plus 2 is 4, or 3 times 5 is 15, is just one tiny island in an ocean of possibilities. Rings are the map of that ocean, and the implications are huge. Rings are at the heart of cryptography, which keeps your messages safe on the internet. They shape how we think about symmetry, structure, and even the deep building blocks of the universe. It's like discovering that arithmetic is not just one story, it's an entire library of stories, each with its own characters and rules. Now here's the twist. In rings you can't always divide. Imagine you're used to slicing a cake into equal parts. In some rings you try to divide, and suddenly the knife just stops working. Division isn't guaranteed here. That small shift makes these worlds of arithmetic strange and beautiful.
Have you ever been stuck with a problem where the usual numbers just aren't enough? Imagine someone asks you, "What's the square root of 2?" On a calculator, you'll see a long, messy number, 1.414, and it keeps going forever. But what if someone asked you for the square root of 5? That's even messier. Or worse, what if they asked you for the square root of -1? Suddenly, ordinary numbers throw up their hands and say, "Sorry, I can't do this." That's where field extensions come in. They're like building a bigger toolbox, adding brand new numbers whenever the old ones aren't enough. Think of it like cooking. At first, you only have salt, sugar, and flour. You can make some simple things, but one day you want to make chocolate cake. You realize you need cocoa. Without cocoa, cake just isn't possible. Field extensions are the cocoa of mathematics. They give you the exact ingredient you need to make the recipe work. Let's go back to that strange question, the square root of -1. Long ago, people thought it was impossible. How can you multiply a number by itself and get something negative? But instead of giving up, mathematicians decided to invent a new kind of number, which they called I. They said, let's make a number whose square is -1. This was the start of extending fields, taking the old number system and adding new roots to it. And once you allow yourself to invent I, the world opens up. Complex numbers appear, like 3 plus 2i, or -1 plus 5i. These are numbers with two parts, one real and one built from I. Suddenly, questions that once had no answers become answerable. Equations that were broken start working again. It's like discovering that your kitchen has a secret pantry filled with spices you didn't know existed. But here's the twist. Field extensions don't stop with square roots. You can keep adding whatever root you need. Want the cube root of 7? No problem. Build an extension. Want the fourth root of 10? Add another. Each time, the world of numbers grows bigger and stranger. It's like climbing a staircase where every step reveals a brand new floor filled with numbers you couldn't even imagine before. This isn't just play, though. Field extensions are at the heart of some of the most powerful ideas in math. They explain why some equations can be solved neatly with formulas while others can't. They connect to the work of Évariste Galois, a young genius who showed how extensions hold the key to solving polynomials, and today they're quietly running behind the scenes in modern cryptography, the math that keeps your bank account safe and your messages private. Think about that for a moment. Every time you log in, every time you buy something online, every time your phone secures a message, field extensions are whispering in the background, making sure the impossible becomes possible. Strange roots, invented numbers, worlds beyond the ordinary, all quietly shaping the digital age. So next time someone tells you numbers are fixed and rigid, remember this, they're not. Numbers are alive. They grow when you push them. They stretch when you challenge them. They extend themselves to answer the questions you dare to ask. And in doing so, they remind us that mathematics is not about limits, it's about freedom. Have you ever wondered how your phone can send a secret message across the world and no one, not even the cleverest hacker, can easily read it? The answer doesn't lie in guards, walls, or locks. It lies in math. But not the everyday math of counting apples or subtracting candies. This is a special kind of math built inside tiny closed worlds called finite fields or Galois fields. Let's imagine you live in a small village where there are only 7 houses. If you keep walking past the 7th house, instead of finding house number 8, you find yourself back at house number 1 again. The whole village loops around. Numbers in a Galois field behave just like that. Instead of stretching out forever, they wrap back around after a certain number. You can add, subtract, and multiply inside this little circle of numbers, and everything stays neatly inside the village. Nothing escapes. At first, this might sound strange. Why would anyone want math that loops instead of going on forever?
But this looping is not a bug, it's a feature. Because once numbers are trapped inside this circle, something magical happens. Arithmetic becomes both predictable and very strong. It's like building with Lego bricks. Each brick has a clear shape, and no matter how you connect them, you know exactly what you're going to get. Here's where it gets even more interesting. If the number of houses in your village is a prime number, like 5 or 7 or 11, then this looping world becomes extra powerful. Suddenly, division works in a very clever way. You can always find a partner number that undoes multiplication. For example, in the village with 7 houses, if you multiply house number 3 by house number 5, you get 15. But since the village loops, house number 15 is actually house number 1. That means 5 is like the magic key that unlocks 3, because together they circle back to 1. This idea of finding the special partner number that undoes another is what makes Galois fields so useful. Why does this matter? Because secrets in the digital world depend on it. Every time you send a password, swipe your card or whisper to your phone through a message app, math is hiding behind the curtain. Galois fields are the stage where this secret play happens. They make it possible to scramble information so that only someone with the right key can unscramble it again. Without these finite worlds, cryptography, the art of secret writing, would collapse like a house of cards. But there's more. These fields aren't just about hiding secrets. They also keep information safe when it travels. Imagine sending a photo to a friend. If one little piece of the photo gets lost, Galois field arithmetic makes it possible to rebuild the missing piece without anyone noticing. This is how CDs, QR codes, and even satellites protect information. It's like a safety net woven out of numbers. Take a moment to reflect on this. In a world that feels infinite and messy, safety and order come from little villages of numbers, locked in cycles, obeying rules that never break. From the outside they seem small, but inside they carry the power to protect billions of lives, messages, and secrets every single day.
Imagine you're holding a flashlight in a dark room. The light shines in one direction and it helps you see where you're going. But the beam doesn't just move straight, it can rotate, twist, and point at different angles. Now imagine trying to capture all those movements, not just with arrows or simple numbers, but with a whole language of numbers that can describe every possible shift and turn. That language is what we call Clifford algebra. Most of the time, when people think of numbers, they imagine simple things, 1, 2, 3. Even when we stretch a little further, we might add negative numbers, fractions, or even imaginary numbers like 1 plus I. And when mathematicians got even more creative, they invented Quaternions, numbers with 4 parts that could capture rotation in space. But Clifford algebra goes further. It doesn't just describe rotations, it builds a toolbox for entire spaces where numbers can hold meaning about points, lines, surfaces, and even higher dimensional shapes all at once. Think of it like this. Suppose you want to explain where a car is and how it's moving. Regular numbers can give you the speed, 50 miles an hour. Complex numbers might help you show direction, say turning left or right. Quaternions can take care of spinning and rotating the car in 3 dimensions. But Clifford algebra, it's like giving you the full map of reality, the car, the road, the curve of the road, the slope of the hill, and even how the air around the car is swirling. It's a number system that doesn't just say where something is, but also how it sits inside the world. To make this simpler, let's go back to blocks. Imagine you're building with little cubes. Each cube is a simple piece, but if you glue 2 together, you get something larger, a blocky line. Glue 4 into a square, and you've got a surface. Stack them higher, and you form a cube. Keep building, and you can imagine shapes we can't even see with our eyes, higher dimensional objects. Clifford algebra works just like that. It starts with simple units, like little blocks, and then allows you to combine them into lines, surfaces, volumes, and beyond. And all of this is captured inside its version of numbers. This might sound abstract, but it's closer to daily life than you think. Computer graphics, like the kind that make video games or movies look real, often rely on these kinds of numbers. When a character spins around, jumps, or twists, the computer needs a language powerful enough to handle all those motions without breaking. Clifford algebra is one of the secret tools behind the scenes. It helps machines keep track of how objects move, collide, and change in 3-dimensional space. But here's where it becomes truly mysterious. Clifford algebra shows us that arithmetic isn't just about counting apples or adding coins. Arithmetic can stretch into a universe where numbers act like shadows of geometry itself. Numbers can carry meaning about space, shape, and motion. They can tell us how a plane tilts, how a sphere rolls, or how a cube spins through the air.
Numbers stop being flat symbols on paper, and they start becoming living descriptions of reality. Take a moment to reflect on that. When you write down a number, say 3, you might think it's just a symbol, but Clifford Algebra whispers, what if numbers could hold whole worlds inside them? Worlds of direction, of space, of interaction. Numbers that don't just measure but explain. And yet, just like many of the strange systems we've been exploring, Clifford Algebra doesn't play by ordinary rules. Multiplication here isn't always straightforward. Sometimes the order in which you multiply matters. Sometimes shapes cancel each other out, like shadows overlapping until they vanish. Sometimes new objects appear, shapes we couldn't have guessed until the algebra reveals them. It reminds us that arithmetic is not fixed. It is flexible, creative, and alive. Clifford Algebra is a reminder that numbers aren't a cage, they are a canvas. They can stretch, bend, and reshape themselves until they hold the very essence of space itself.